Guys. We're going to be talking about properties of matter. Chemical properties and physical properties are two of the ways that we discuss matter, talk about matter, as well as chemical and physical changes. So let's just look real quickly at the difference between the physical properties and chemical properties. So physical properties, as I've written for you, can be determined without changing the chemical composition. So those are the things that you do every day when you see something. You observe physical properties. So real quickly, physical properties could be appearance. They could be color, which includes appearance, of course, texture. We could taste, not that we do that in chemistry lab, but tasting would be a physical property. We could smell of them. So odor is a physical property. Melting or boiling point is a physical property. Density is a physical property. Any of these things, to look at them, to look at the substance, to observe the substance, to calculate its melting, boiling, or density, none of those things are going to change it chemically. The solubility in water, in other words, checking the solubility of something, it could also be the solubility in another substance other than water. It could be ethanol. Solubility, though, is a physical property. It is not changing the chemical composition. So anytime we check a physical property of a substance, it is not changing the chemical composition of the substance, so the physical property is a physical property. Chemical properties are going to change the chemical composition. And basically what you're doing when you're talking about chemical properties is you're describing the substance's ability to make new substances. And so what we might say, for instance, in regards to a chemical property, is we might describe how one substance, when reacted with another substance, changes to a new substance, and that would be a chemical property. So just an example of a chemical property is sodium reacts in water and produces sodium hydroxide and hydrogen gas. And that would be a chemical property of water. And what you see when that occurs is you're going to see bubbling with that occurrence of the hydrogen gas. So if we were to write this out as an unbalanced equation, I'm not balancing this, this is an unbalanced equation, but this is what we would have. So Na plus H2O yields NaOH plus H2. And we would put a little G there for gas because that would be a gas. This is liquid water. This is solid sodium. And then this is an aqueous mixture. And we'll talk more about those terms in a little bit, but those would be an unbalanced equation. This is an unbalanced. We'll make a note there that that is an unbalanced equation that I've written. But that is describing the chemical property of sodium when it reacts in water. And that's what that equation represents. Physical and chemical changes are changes that are showing these physical or chemical properties. So we may ask you in many different scenarios to actually describe if something is a physical or a chemical change. So let me just describe for a moment if something is a physical or a chemical change. So the rusting of iron, for instance, if I said something about rusting, that would be a chemical change. And how do you know that? So here's one of the things that I want to encourage you to do. That list of separating mixtures, the ways to separate mixtures that we gave on another slide, that information helps you know if something is a physical or chemical change. So when you think about a change, such as rusting, think to yourself, is rust a new substance? Could I identify it as I did the original substance. Is it a physical change or a chemical change? If it's a physical, then we've got to think, okay, can it be separated from the other thing in a physical means? So think of rusting. What about a substance that is not rusted? It's going to be picked up by a magnet, all right, because iron is what rusts. So let's take rust itself. Can rust be picked up by a magnet? And the answer is no, because it's a chemical change. It's a new substance. Now, do chemical changes often have an accompanying physical change? And the answer is yes, because what happens is rust, for instance, is reddish in color. The iron nail may have been a very dark black gray color. Are they different in colors? Yes. Is that a physical difference? Yes. But what caused it? It was a chemical change. What if I just boil water? Boil water, boiling anything is going to be a physical change. It does not change the chemical composition. What about if I just saw a piece of wood or tear paper? Both of those, again, are going to be physical changes because I'm not changing the chemical composition of those. Now, what about boiling an egg? Now, in that scenario, use your nose. And I realize, well, using your nose is I thought you said the odor of something is a physical property. Yes, it is. But does a boiled egg smell the same as a raw egg? And the answer is no. Why is that? Because it's a chemical change. There is a true chemical reaction taking place that causes that egg to smell different, and that's where you get that sulfur smell. And so it is definitely a chemical change. What about burning anything? Any kind of burning is a chemical change. Anytime you have burning, that's a chemical change. What about melting glass or blowing glass? That would be a physical change. That would be a physical change. What about let's see, burning anything? Combustion of gasoline is the same as burning. Let's see, there was one I was trying to think of that is a little confusing. And, oh, digestion of food. What about digestion of food? Digestion is going to be chemical. Think about what that comes out like and how it went in. It's not the same. So that would be chemical. Digestion is definitely chemical. So if I paint a wall, what would that be? That's a physical. Physically changing the wall. Painting, that's physical. So you think of some different ones that are, and I'm sure you'll be able to come up with different physical and chemical changes. All right, we've got two laws we want to talk about now that we have that will help us understand a little bit more about matter. So let's talk, and really, well, one of these will help us understand matter. The next one is a law about energy, which gets us started into our last topic before the exam. So the law of conservation of mass is one that you've heard before, and it tells us that matter cannot be destroyed in a chemical reaction. Matter cannot be destroyed in a chemical reaction. And that's why I say up here, what or the mass that goes in must come out. That means what goes in must come out, or the mass that goes in must come out. And what that basically means is the mass of the reactants must equal the mass of the products. What goes in must come out. So let's just take an example here. If I have a reaction that makes sodium chloride, and if I said to you 14 grams, this is my example, 14 grams of sodium reacts with chlorine to produce 64 grams of sodium chloride. How many grams of chlorine reacted? Well, if 64 is your mass of the product and your reactants are both sodium and chlorine, then you just need to find chlorine by taking 64 minus 14. So 64 minus 14 equals, and the answer is 50 grams. So it's 50 grams of chlorine would be reacted. Another law that's very important that sounds similar to this is the law of conservation of energy. And that law states that energy can be neither created nor destroyed in a chemical reaction, though it can change from one form to another. So energy can be neither created nor destroyed in a chemical reaction, though it can be changed from one form to another. What is our greatest source of energy? It's the sun. What does the sun do? The sun shines down on the plants, causes the plants to grow. So the plants get energy from the sun. The plants then are a source of energy for humans, for animals to eat. What does human do then? Human comes along and eats the animal that got its energy from the plants, that got its energy from the sun. All right, take another route. We get our energy directly from the plant. So then we immediately have our energy from the plant that got its energy from the sun. We have our energy from the plant, and then what kind of energy do we have because of that? Do we glow? No, we don't glow, but what do? We move. So we have energy that allows us to move, so that food energy changed into energy due to motion. Do we create heat? Yes, we do. So that energy from the food that came from the sun is now changing into heat energy. And so you see this, it just goes on and on. What about sound? Do we have sound? Do we make sound? Yes, so part of that food is changing into energy that changes into sound energy. And so we're constantly changing from one form of energy to another, but the total amount of energy is constant. It cannot be created or destroyed in a chemical reaction. All right, so let's look at two simple types of energy, really simple. This is old school. Energy, the study of energy is a physics class. This is not a physics class, this is a chemistry class. So I'm going to keep this super simple. Kinetic energy is energy due to motion, movement is kinetic energy. Potential is energy due to position. Or we could also say stored energy. So battery energy, for instance, would be stored energy. Water behind a dam would be also due to position, so that would be a potential energy. And so think about those two types of energy in just simple situations. For instance, if you're a child rolling down a hill, what energy do you have at the top of the hill that's the greatest? And then what energy do you have as you're rolling? So your top of the hill would be more potential energy. And then as you start rolling faster and faster, that potential energy changes into kinetic energy. And at the bottom of the hill, you make a splat sound, you don't make any sound, but you still have potential energy, and then you've transferred your energy throughout that roll. And so think about things, rubber bands, when you pull the rubber band back, some of you may have had rubber band cars. Think about just, again, our food energy is transferred, it's stored energy, potential energy, then we eat, and we have kinetic energy. So constantly changing into those different types and forms of energy. In our class, what we're mainly concerned with is energy that's due to heat, or the heat energy, and we're going to use that specifically in what we call the heat equation. Now, I've added some different labels to this equation than what you actually printed. So you want to add to this heat energy, which is in another format. You can write heat energy as Q, and this doesn't mean heat times energy. This means heat or energy. Same word. This is not times, okay? I didn't want to make you think that. Heat or energy is equal to mass times specific heat, which is symbolized with C, because it's specific heat capacity is what that's called, times the change in temperature, which is delta T. So the formula is Q, which is heat. So this is Q equals MC delta T. That's how you would see this in another book probably. For us, I make it super simple and I just say heat for Q, and I could also have written energy there, is equal to mass, which I write in G because it needs to be in grams for our purposes, SH, specific heat, times delta T, which is change in temperature. Describing this a little bit more, heat or energy will be in units of joules, calories, or big C calories. This is the food calorie. All written right here for you. So 1,000 small C calories is 1 big C calorie, or 1 kilocalorie, and that is an exact conversion factor. And 1 calorie is exactly 4.184 joules. So these are 2 conversion factors that you will want to add to your list. Let me explain again what I mean by this. When you're dealing with heat or energy in this equation, that means when you're dealing with heat or energy, which is what this means, heat or energy, when you're dealing with heat or energy in this equation, the units will be joules, calories, or big C calories. And this is how you could convert between joules, calories, or big C calories. Mass must always be in grams. That's why I put G in my shorthand equation that you do need to memorize. Specific heat is the quantity of heat, either which is why the units for specific heat are joules per gram degree Celsius, 3 units, or small c calories per gram degree Celsius. Again, note, joules and calories are the heat unit that we're discussing here per gram degree Celsius. That is what specific heat is. So if you look at a chart of specific heats, the glare so much. Water has a very high specific heat. So water has a specific heat of 4.184 joules per gram degree Celsius, alcohol less, ice less, aluminum 0.9, iron 0.28. Now, what's happening? They're going down. Well, let's talk about something for a minute. What are aluminum, iron, copper, gold, and lead? What type of element are they? Every one of those is a metal. What are metals good at? Metals are good at conducting heat. So would it make sense if these are metals are good conductors of heat? Would it make sense that it wouldn't take much energy to change their temperature by 1 degree Celsius? Think about that. Think about that. Think about, would it take much energy? No. That is why you see this specific heat just decreasing, and it's so much lower than something like water, for instance, which then makes you think, well, is water an insulator for heat? Yes, in essence, it is. In fact, why do we use water to put out fires? We don't use water to put. I mean, the purpose of the water is to cool the fire down. Water literally can take the heat. I've often said that should be a t-shirt. Water can take the heat because it can. Water can truly take the heat. To give you an example of how water can take the heat, think about if you're trying to boil water. You put a big pot of water on the stove in order to make your spaghetti. Well, does it heat up just immediately? Or your water? Well, you know the answer. The pan heats up extremely quickly, and then the water will eventually heat up and boil. But which one heated up faster? The one with the lower specific heat. Which one heats up more slowly? The one with the greater specific heat. Now let's go reverse of that. You have a spoon in that pan, and it's a metal spoon, and you have left it in there. Your water is boiling, and you grab the spoon. Ouch, immediately. Why did you grab the spoon? Because you weren't thinking. Why was it hot? Because it has a low specific heat, and it was able to change temperature so easily. So you take the spoon out and you set it over on another container on the counter, let's say. In just a few seconds, few minutes, that spoon's going to be cooled enough to touch because it doesn't have a high specific heat. Now let's take that water on the other hand. That water just a long time. Have you ever had a cup of coffee that's too hot or a cup of hot chocolate? And it takes a very long time for it to cool down. Why? Again, because it's the specific heat of water. Water has a very, very high specific heat. Same thing again, let's think about swimming and going to the beach, going to the pool. In the water, still a high temperature. It's about 82, and that was yesterday or last night. That's really high when the nights are still getting down to like 60. But the water in the swimming pool is going to stay warmer for a longer period of time now because it it will take so long for it to cool down because high specific heat, and it takes a lot of energy to change that temperature by 1 degree Celsius, which is what specific heat is. So hopefully that explains a little bit more about specific heat and what it is. Now, for our purposes, we are going to do math problems. So we're going to take that equation and we want to understand specific heat, but we also want to be able to do the math. And so let's look at the math problems that before I start that though, let me point out you are responsible for knowing the specific heat of water. So again, add this to the of water, except the units are different in calories. So the specific heat of water is 1 calorie per gram degree Celsius or 4.184 joules per gram degree Celsius. So this is the specific heat of water. And so that is always absolute, which means it's positive. And it will always be in degrees Celsius. So the change in temperature is always a positive change, and it will always be in Celsius. So if I give you, let's point out, if I were to give you, and I don't think I do that on any of the problems today, but degree Fahrenheit or Kelvin, what will you do? You must change it to degrees Celsius because the units for specific heat deal with degrees Celsius. So the first problem, let's simply calculate specific heat of a solid. First thing I want to do is I want to write down my equation. The equation is heat equals mass, and I'm going to write out the whole thing to start with. Mass times, well, not the whole thing, but almost. Mass times specific heat times delta T. So we're looking for specific heat. So we're looking for SH. What do we know? We know 1638 joules. What is that? That's the heat. We know grams. So I believe that's 27.6, but let's do the math. 52.6 minus 25, and that is 27.6. So plugging it in, 1638 joules equals 125 grams times specific heat, which is what I'm looking for, times 27.6 degrees Celsius. Now we're just solving for specific heat. If you want to call it X, call it X. I don't care what you call it. We're solving for specific heat. So 125 grams on both sides. You're going to see where the units come from right now. 27.6 degrees Celsius, both sides. And notice the units. There's nothing that's going to cancel out. So it's joule per gram degrees Celsius. So plug that in your calculator. 1638 divided by 125 divided by 27.6. Remember, both of these are divided. Do not waste your time multiplying this, then taking this divided by that, what you just heat equals 0.47478, yada yada. Significant figures are going to be, and we have to follow all the rules, so there's 4, 3, and then that subtraction ended with 3. So 3 is the least, so that 7 will come up, so the specific heat is, and that is your answer. All right, let's look at another problem. Now, in this problem, I threw in all kinds of work for you to do on this problem. I probably made it possibly a little too hard for the second problem, but I know you can do it. So let's look at it. It's asking for big C calories, so now that automatically should trigger kind of a, wait a minute, I'm probably not going to get it in big C calories because that's not a normal unit for specific heat. I'll probably get it in little c calories and then have to convert it. But it says how many calories will be burned by drinking 1 quart of water at 5 degrees Celsius. Now, why am I saying it's going to even take any calories? Celsius. So you're going to have to heat that water up, and that burns calories. So maybe if I wanted to lose weight, I should just always start drinking really cold water or eating ice. Just a thought. All right, so now then, let's see. Wait a minute, it's got quarts. Quarts doesn't give me mass. Oh man, I've got to do dimensional analysis. Oh yes, I get to do dimensional analysis. So let's look at that. So how are we going to do this? We have to determine the mass. This is volume. What do we have to do to get mass from volume? We have to have, wait a minute, let's stop. Why do we even need to know mass? How do you know you need to know mass, Miss Brooks? Because what's it asking for? It wants to know heat. What's the equation? Heat equals grams times specific heat times delta T. Do I want to find heat? Yes. Do I have grams? No. I have volume. Well, it doesn't give you specific heat either. However, what are we doing? We're drinking what? We're drinking water. So what specific heat are we needing? We need the specific heat of water, and that's calorie per gram degrees Celsius. So what do we know? We know specific heat of water. We know change in temperature is going to be 32 degrees Celsius. We don't know the mass, and we want to find heat. Do I have something that will get me the mass and the is 946 milliliters. And what is that nice little step to get us into mass from volume? It's called density. And so the density of water is 1 gram per milliliter. This is the density of water. Remember, you're supposed to know that. And that gives us what? That gives us I think we can do this one in our head. 946 grams is the mass of water. So 946 grams is the mass of water. So now then let's plug it into our equation. So heat equals 946 grams times 1 calorie per gram degree. 5 is 32 using proper significant figures. So that's 32.0 degrees Celsius. Notice our units canceling. Grams cancels grams, degrees Celsius cancels, and we're left with calories. So you're going to take 946 0.0272 small c calories. But the question did not want small c calorie, it wants big C. So we have to convert 1,000 small c calories is 1 big C calorie, and then you get 30.272 big C calories. Significant figures, how many do we need in our final answer? And that is 1. I'm sorry, that's 2. It comes from 1.0. So what did you just figure out? What you figured out is if you drink 1 quart of really cold water, your body is going to have to burn 30 calories to warm that water up. So, pretty cool. All right, let's look at the next one. Another problem dealing with specific heat. The only real difference here that I see compared to the first problem we did is that you are going to have to deal with this kilojoules, which means so it's 866 kilojoules, that's energy, to change from 22 to 100 degrees Celsius. What is this specific heat? This is the same type problem as the very first problem we did. It's just a little trick because you have to deal with kilojoules. So kilojoules, any kilo is the same. Problem. I'm going to put my little side problem over here. 5.866 kilojoules. 1 kilojoule is 10 to the third joules. So what would happen to that then? Pretty easy to do that. I'm just going to leave it in scientific notation. So now I'm going to write my formula down. Heat delta heat now. 5.866 times 10 to the third joules. So 5.866 times 10 to the third joules equals, my mass is 250.0 grams. My specific heat is what I'm calculating, and my change in temperature is 78 degrees Celsius. Where did I get that? The difference. Okay, that's where the 78 comes from. All right, same math that we did earlier. Let's plug it in. So specific heat is 5.866 EE3 divided by 250 divided by 78. And on your calculator, you should get 0.30. Want to think that you can use 4, but be careful. This had 4, I agree. This had 4, I agree. However, these are only precise to the ones, which means when you do the subtraction, it's still only precise to the ones, and that has 2 significant digits. So your final answer may only have 2, which is 0.30, don't forget the units, joules per gram degree Celsius. Remember, nothing canceled out in this it's on a conversion. And again, if you need to show the math, look up at the top here what I did. Same thing. That's exactly what you would be doing. I just did not show that again the second time. I'm assuming you know how to do that. All right. So we want to know how many bars are needed to heat water. Well, we know how much water. We know the temperature change. We should know the specific heat of water, so let's go ahead and write that down. 1 calorie per gram degree Celsius. But some of you are asking, what about the granola bar? Don't you need to know that all for the granola bar, not for the water? No. For just a minute. What is most of the food used for in your body? It's not to make your heart beat. It's not to make your brain work. What is most of the energy that you consume used for in your body? It's to keep you warm. Most of the energy is to keep you warm. If you know someone who doesn't eat enough, and I hope it's not you, I hope you are eating enough. But if you know someone who has an eating disorder and they don't consume enough calories, they are probably always cold. Why are they always cold? Because to keep your body warm. Babies especially need to be kept warm. You want all the food that you give a baby to go to its brain development and growth. You do need enough food to keep the baby warm and develop. But overall, you want to make sure that a baby consumes enough calories. If your baby is on formula, don't get cheap. Don't cut the formula in half because you want to be cheap and save money on baby formula. All you're doing is hurting your child. You must have enough. Or you need enough calories to do that. All right, so we're using this granola bar to heat up water. That's what we're mainly doing in our body, is we're heating up all the water we have. So what we want to know is how many bars of granola bars are needed, but what we really need to know first is how much energy is needed or how much heat is needed. So that's our first question. So the equation is exactly what we thought. To begin with, heat is grams times specific heat times change in temperature. And then we can convert it to granola bars since they have energy, which is heat, a source of heat. All right, so this could be, anyway, make sure you know, anytime I write heat, I could have also written energy. It means mass. Our mass is 3.8 times 10 to the third grams times 1 calorie per gram degree Celsius. Is 28.5 degrees Celsius. Again, we can see our canceling units, and that's going to leave us in calories. So run your numbers. So that is 3.8 EE3 times 28.5, and you get small c calories. So what that means is it takes 108,300 calories to heat up 3,800 grams of water. That's what this is. That's also 3. Does that help you see the big picture? How do I know all of what I just said? Because grams per milliliter, 1 gram per milliliter, that's the density of water. So if I'm talking about, and 3.8 times 10 to the third is 3,800. So 3,800 grams of water is the same as 38 milliliters of water, which is very close to 4 liters. It's 3.8 liters of water. So imagine now that much water. We will need 108,300 calories to heat that much water up. Now, if you're wondering, what about this small c calorie and all the diet stuff? And I thought, we're like 2,000 calorie a day diet. Well, diet, we're talking about 2,000 big C calories, which is 2 million small c calories. So this one bar that contains 100 big C calories, that really is 100,000 small c calories. So let's see how many of those bars we need. So we're going to convert this into big C calories. So it's 1,000 small c calories into 1 big C calorie. And then our bar is 100 big C calories. So if we do the math, and many of you can just run through and figure out this with looking at our zeros and dividing there, but if you can't, then let's look at what we get, and you get 1.083 bars. That's what we would get on our calculators, 1.083 bars. All right, significant. And the final answer would be 1.1 bars. So it only takes a little over 1 bar. A little over 1 bar. That's only 100 calories to heat up all. So pretty interesting question. Pretty interesting question. So going back to this one that we talked about earlier, is that similar? Yes, it is. This is a very similar question. And you could even look at the temperature changes are not that much difference, and then compare a quart to a liter. So it was 30 calories for 1 quart. Would it make sense that it would be 100,000? This is 30,000 calories. Does that make sense that this would be 100,000 calories for see if you can figure out what I'm talking about there. I think you can. I know you can. All right, last question is very similar to the one I've just done, except this time we're talking about a power plant. And we're looking at coal, and coal is being used to heat water. So how does a power plant work? A coal-fired power plant works by coal, or a fossil fuel power plant. You heat up water, which then in turn turns to steam, and the steam then turns a turbine, which then turns a generator, which generates then electricity. And so let's real quickly go back here for just a minute though. Where did the energy come from? The energy came from the coal. Where did the coal get its energy? Coal and natural gas are stored energy. Where did that original energy come from? Shine down on the earth and shined on the plants and caused the plants to grow. Dead plants, dead animals that ate the plant, that grew, then died, dead plants and dead animals buried in the earth. The dead plants and the dead animals into coal. So what happens is it all goes back to the sun. So does our electricity now come from the sun ultimately? Yes, it does, because it comes from the coal or the natural gas. Now, nuclear, different scenario. From the sun and that whole energy cycle. All right, so let's do this problem. So this time we know instead of having a granola bar, we have coal. And it's 1 gram of coal giving off 7,000 calories. Earlier in the last problem, it was 1 bar giving off 100 big C calories. So you see, this is a conversion factor. 1 gram of coal gives off 7,000 calories. The question is, how many grams of coal are required to raise the temperature of 4 liters of water from 20 degrees Celsius to 100 degrees Celsius? This problem is exactly the same as the other problem. Water, shouldn't we be worried about the water? Look, I've prepared you for this. Back here. Did you have a problem that you had volume? And what did you do to find grams of water? Did dimensional water. We need to get this from volume into mass. So let's put what we know. Density of water, 1 gram per milliliter. Specific heat of water, 1 calorie per gram degree Celsius. About how much heat we need, it's the same problem as the granola bar problem, except you have to convert your volume of water to mass. Guys, I'm building upon everything we've been doing this semester so far. What have I told you? Chemistry builds upon itself. You've got to remember dimensional analysis. You've got to remember using density as a conversion factor. And this problem pulls so many of those things together. So let's look at it. So let's take, first of all, we're going to figure out our mass. We're looking for mass of water. So to do that, we take our 4 liters, and I'm sorry, it does not have an extra 0, so forgive me on that. 4.0 liters, that's a mistake. That just forget that there's another 0 there. 4 liters, 1 is 1 gram per 1 milliliter. So what do you get? I think you can do that in your head. 4 times 10 to the third is 4,000 times 1. So what do we have? We have 4,000 . grams. So 4,000 grams. And that is the mass of water. The change in temperature, I think you can see, is going to be 80 degrees Celsius, and we know the specific heat. So the question is, how much heat do we need to heat this much water? How much energy do we need? So it is going to be mass, so 4,000 grams times 1 calorie per gram degree Celsius times 80 degrees Celsius. Probably can do that without a calculator. Just to make sure we get all those zeros right, we're going to use the calculator. 320,000. Remember our units here so that you end up with small c calories. So the amount of energy to raise the temperature of 4 liters of water from 20 degrees Celsius to 100 degrees Celsius is 320,000 calories. Remember, water has a lot of energy. 1 gram of coal gives off 7,000 calories. So all we have to do now is take our 320,000 calories, that is the energy needed. We know that 1 gram of coal will produce 7,000 calories. So that tells us how many grams of coal. So 320,000 divided by 7,000. And so we have density is 1 gram per milliliter. That's density is 1 gram per milliliter, so that's 3 significant figures. The specific heat is 3. We had only 2, though, for volume. So of coal. Now, a gram is tiny, folks. That's what I'm trying to get you to realize. That is not much coal that produces that many calories. Pretty amazing. 46 grams of coal. Glad we don't eat coal. It's extremely calorific. Out watching me at the same time. These on your own, and hopefully you can follow through and understand these. Hopefully you understand the concepts here. Give you just a rundown of what to expect, some of what to expect on that first test. Study your notes. Study your notes. So that's what